Good. Fantastic. Okay,
right, so
recording is back. Okay, so let me introduce you again. It's my great pleasure once again to welcome Ivo Sachs from Munich, talking today about a toy model for string field theory. Okay, take it.
All right. So, well, thank you very much for the invitation. So it's a pleasure to be in Prague. So, yeah, so I guess this is going to be quite informal. So please treat it as an informal. Ask any moment. Also, I'm not sure. Some of your background I know, some I know a little bit less. So I might be talking about things you know already very, very well, or that you're completely unfamiliar. That's fine. So just let me know. I'm happy. Actually, I didn't really prepare too much also for that reason, because I figured we just let it go where the talk takes us. So that's the idea anyway. So yeah, so the thing is, my motivation for all this is that I've been working on string field theory for a while, and I wanted to understand what the issue of background independence in string theory. This has been a long story. I will not say much about string theory here, but I will really mostly use it as a motivation. But still, so what I wanted to do in a way is to do string field theory in a background independent way, and I still have no idea of doing it. But so instead, I decided to do something simpler, which is the point particle, which is similar to the string field theory. So that's where the word toy model comes from. It's a simple version of string field theory, almost trivially simple. But nevertheless, it gives some ideas of how things work or what doesn't work. So that's a little bit the story here. So, but just to give you the setting is, what we do think is that string field theory, we know it has a huge amount of gauge symmetry or some invariances or redundancies. And usually the way to describe such things is in the BV formulation. So the BV formulation seems to be the most general way we know how to describe gauge theories, or also generalized gauge theories, where the constraint algebra doesn't necessarily close. So then we would need it. Now, of course, we can use BV formulation for Yang-Mills theory, but we don't really need it, although it can be very useful for some issues of Yang-Mills theory. But once you go beyond Yang-Mills theory, where you don't really know what the constraint algebra is, or the gauge symmetries are, then BV seems to be the right formulation. So therefore, it seems that string field theory should be somehow, if it's a field theory at all, it should be somehow fit into this BV formulation. So therefore, what I will do is I will start with introducing a little bit of BV, just as much as I need, and then see how it relates to string theory, and then take it from there. So let me just do maybe drawing. I hope you can see what I do here. So let's assume that this is some configuration space or field space. I'm going to write a configuration space, and then denote it by F. So that's where all the fields would live. So it can be a graded space of fields, which can include ghosts, all sorts of things. I don't need to assume that they're all parity even. So, and then, so that would be some data. And then in the BV formulation, you assume also that you have a BV differential delta, which is a second order differential that so squares to 0, but is a second order, it's not a first order differential. And so you assume you have this, and typically one we also assume that there is an action. So an action functional, so let's say S, which is a functional from F into say R or C. We can take C for that matter, it's not so important. And so it associates to every field configuration some number. So this would be the action function. And so we have this triple, so we can say that somehow BV would be this triple, which is a space of fields. We have this BV differential. I will say a little bit more about it later, but not quite yet. And this action functional. So this seems a very general setting. Of course, doesn't say too much yet. So how is it related to gauge theories? So how is it related to? So let me say relation to gauge theories. So what we do is we take e to the action. So maybe I can take it in the Euclidean section, doesn't matter. So put your plus, sorry, and then I take this second order differential, e to the minus 1 over h bar s, and I can just compute it. And so that gives two things can happen. Since it's a second order differential, since I have two derivatives, what can happen is either both derivatives hit the s, or both derivatives hit the exponential. So I get two terms, right? So I get a term, which I will just define it perhaps in this way as s comma s. So that's quadratic in s, plus, say, a h bar, and then I should probably put some 1 over h bar in front. Let me remove that just to get it right. Should probably be something like a minus 1 over h bar, if I didn't get it wrong, plus, say, delta h bar delta s. So, but that is where the both derivatives hit the s, and here you get twice the usual thing. I mean, differentiate twice. So this is what is usually referred to as the BV bracket, and it actually expresses gauge invariance. So expresses gauge invariance of the action S. And then this is sort of the quantum consistency. I will actually say almost nothing, probably nothing about quantum consistency today. But so if h bar is equal to 0, this expresses the gauge invariance. So let me just say that again now. So we have basically the statement that if you have this action S, which introduced, so if it satisfies S comma S equal to 0, so that is tantamount to gauge invariance. And we know what that means, right? So if you take, for instance, Young-Mills theory, we can use a BV formulation for Young-Mills theory, and then we will find that we can form this master equation is basically saying that the theory is gauge invariance, encoding it. But it also allows for generalizations of it. So depending here, that's where you introduce anti-fields and all sorts of stuff. And depending on how this action, so maybe let me write this also just as a comment, perhaps as just a remark. We could say S is equal to S0, which is often called the boundary condition. Then we have things which are of the form, say, gauge transformations times anti-fields. So let me write here phi star, some anti-field. And then you could also have things which are perhaps of the form anti-field squared. And that is where you go typically beyond gauge theory, when this action depends not just on the fields, but also to higher order in the anti-fields. Typically, that's not a gauge theory in the usual sense. Okay, so that's sort of my crash review of BV formulation. Are there any comments or questions about this? So just go ahead. No? Okay, so I'm not actually going to use much of this. All I wanted to take home from here is that I want to assume this structure for a little while, that I have this structure of a space of fields, this BV differential and S. So now the thing is, what I can do is, write that perhaps over here. I'm going to go a little bit away. So, like this. What I can do is I can take, suppose I have some function, let's say A is another functional from F into C. What I can do is I can take this combination S comma A. So that seems like that gives me a vector field. So that seems that I can say this is some, let me write it, omega of A. So since I have already this action functional, I can build this BV bracket of this action function with any other functional A, or function if it's a finite dimensional space. And then this acts like a vector field. So it seems like this, the moment I have this BV structure, this induces, put it a vector field on this space of fields, which I denote by omega. Be like this. So that would be another way of describing BV, is that you have a space of fields, So alternative description maybe. Description is I have F together with a vector field omega, which actually squares to 0 since it's an odd vector field. So then we have also omega squared equal to 0. And that simply follows from the fact that s comma s is equal to 0. You just use the Jacobi identity. This BV bracket, I didn't say too much about it, but it satisfies. It's a Lie bracket in the sense that it satisfies the Jacobi identity. Okay, so that would be another way of characterizing. You have a spacer field with this what's often called the homological vector field, since it's homological vector field. So the thing is now we can study purely geometrically. Now we could say let's study the zero locus of this vector field. So we can ask, what does it mean that omega equal to 0? Not identically 0, but what are the points where omega is equal to 0? So suppose here there's some point, let me denote it by phi 0. And so maybe I'll write this in this way. Let me say, what does it mean that omega at phi 0 is equal to 0, and that the vector field vanishes at this point? Well, if I go back into the definition of the vector field, it seems that means that s comma is equal to 0. Move this a little bit. This is equal to 0. But that is a critical point. So that means that the first derivative of the action vanishes. So therefore, that means we have a critical point. Critical point of S. And so in physics, we often call it the equations of motion, solution of the equations of motion. So we have this geometric vector field omega, which vanishes precisely on the critical points of S. Okay, so now what we could do is we could say, okay, let's linearize this theory. What I'm going to do is I'm going to expand this homological vector field around this critical point. So let's expand it. So I go, move here a little bit. Let me go over here. So I'm going to do now, expand omega around phi 0 on this critical point. So then I would say omega is equal to omega 0. That's actually the vector field at the critical point. So that is going to be 0. Plus the first order in the expansion, plus second order in the expansion, and so on. So I can expand it in this way. Now, if I think of it, I mean, this is obviously an expansion in the tangent space at phi 0. So I can think of omega 1 is a map from t phi 0 of f into t phi 0 of f. And so it's mapped from the tangent space in itself. It's a linear map. Whereas the omega 2 would be more like a map from t phi 0 of f into t phi 0 of f. Sorry, it should be t squared, also in this sense, because it's a vector field that maps functions into in here. So we can have this expansion, or you can always think of it the other way around also. It maps from the omega 2, you can take the dual version where it maps the tensor product of the tangent space into the tangent space. So that's fine. So that seems to be the structure of this BV theory around the critical point. So now I can, however, because it's a homological vector field, so if I have omega squared is equal to 0, as we noticed, that imposes some conditions on, implies, let me write it like this. This implies that this collection omega k, and let me take k bigger than 0, omega 0 I take to vanish, they satisfy, they form an infinity algebra. So it's not, you have higher order maps. Now, this L-infinity algebra make very popular these days, but I'm not actually going to use it. We can just take this to be the definition, doesn't matter. We can take this to be the definition. If you expand the homological vector field around the critical point, simply the condition that omega is homological implies that these expansion coefficients will satisfy. We can take this as the definition of an L-infinity algebra. I'm actually not going to use it. So now, great. So, but we can go a little bit further. We can do one more thing. And this is again not so relevant for my talk, but in connection with string theory, it is useful to know is that since it's a homological vector field, we can look at the cohomology of the linear piece. So let me define. How will I define it? Not to confuse it with other things later. I don't know, maybe like this, if I can do that. So let this be the cohomology of omega 1 of the linear piece. So then there's another fact, which is just basically what we usually call Feynman perturbation theory. So then this is just Feynman rules, or LSZ reduction, all that stuff. Feynman is not so important for us. Is basically saying that this structure of the omega k induces another minimal L-infinity algebra. Let me denote them by Sk, which is another L-infinity algebra. Or let me write a minimal L-infinity algebra. On this cohomology of omega 1. So why do I say? I mean, what's the point? Of course, this is a homotopy transfer. Many of you know this very well, but why do I mention it? I mention it for the following reason, because now I want to make the connection to string theory. Yeah, that's finished, so I have to go then. Yeah, maybe. Now I can do the following things. I can zoom this in. So let me do that. So maybe here we go. I want to bring a little bit more than here. So there we go. So now we have the following structure. I want to summarize. So I want to summarize everything I've said so far. It's a summary. So we have, on the one side, we have this F, delta, and S. So that was the initial data of a BV system. Expansion, this first induces a homological vector field, omega, and then on an expanding around expansion at phi 0 gives me the omega k's. And then finally, using this Feynman perturbation theory, the minimal model map gives me the SK. They live on the cohomology of the linear piece. So now I want to put physics to this. This is where string theory lives. And this makes sense because strings. Because what do we do in string theory? In string theory, we compute S-matrix elements. That's what the string theory is, somehow a very clever machinery to compute S-matrix elements in terms of integrals over the moduli spaces of Riemann surfaces with punctures. I will say a little bit more about it later. But, now, that is where string theory lives. Now, string field theory lives here. String field theory is what you try to do in string field theory. You try to find a field theory which provides the vertices which finally, using Feynman perturbation theory, give these S-matrix elements. So you see, it's somehow in string theory, everything goes the wrong way around. In string theory, we know already what the S-matrix, we have a well-defined procedure how to compute S-matrix elements, but we don't really know the action where it comes from. So string field theory is an attempt to reconstruct the action where these S-matrix elements came from. And we do this, we can do this using the Polyakov actions, Wiebach's construction of string field theory, and all these things. We can do this around a critical point. We have to always assume, say, Minkowski space and then expand around Minkowski space. So we can do it perturbatively, and that is precisely this expansion of the homological vector fields around the critical point. Now, the question mark is, what is this? And to some extent, even what is this? And that gives me my motivation. So I would like to go here and maybe even here. So I would like to see in a truly background independent way, because this, of course, the moment you choose a phi 0, you chose in a background and you expand around a certain critical point. So at this moment, everything becomes background dependent. So I would like to overcome this background dependence and formulate it in a background independent way as a BV theory. So that's basically the motivation, a long motivation for this talk. So let me see, any questions or comments at this point? Put this here, so let me see it. All right. So now the thing is, in string theory, I don't really know how to do this. It's very complicated to do that. So the thing is, it's just it's an infinite dimensional dynamical system. Typically, we cannot handle. So then I think maybe there is this point particle, which is similar in the sense that it is in a certain limit of the string when we take, say, alpha prime goes to 0. So we make the string infinitely tension, the string tension infinitely big, infinite, then we should reduce to the point particle and no excitations of the string anymore. So then I could say, is there a version of the point particle where I can do this? Maybe let me put it in blue here, where I can do this. And the answer is yes. And for the point particle, you can do it. And this is what my talk is going to be about. The one thing, though, you might say, yeah, but wait a second, for point particle, we know, say, let's take a spinless point particle. We know already what the field theory is, so what's the point in constructing something we already know? Then you say, okay, yeah, it's true. You could say for a vector field, say spin 1 particle, we know already is Young-Mills. So what's the point? It's also true. And even for gravity, to some extent, we know already what the field theory is. It's Einstein theory, so, or maybe it's a modification of Einstein's theory. So, you know, what's the point in reconstructing it again? It's true. So basically, I can tell you already now, the result of this exercise will be Einstein theory plus some extra degrees of freedom, which will pop up, or Young-Mills theory, depending on what point particle you start with. But by running this program. So that's basically going to be the outcome. So here we will end up with something, I can write it here quickly, something like Einstein plus other things, or maybe Young-Mills plus other things, possibly. That's what I want to discuss a little bit. All right, so that basically puts gives a framework of what we're going to do. Okay, so now, if we want to mimic this string program for the point particle, we should start with a word line. And there is, of course, a word line formulation of the point particle, but it's got to be relativistic. So let me start with a relativistic point particle. Point particle. So, okay, we can write down a word line action. We write it perhaps as I, the word line action, which will depend on what? It will depend, say, on Q and some metric. I'll write it like this. It will be PQ dot and then minus 1 over E and then the Hamiltonian, where the Hamiltonian is P squared plus M squared. And then integrated over d tau. So this is some parameterization. Tau is some parameterization. So we have some parameterized curve. And tau is the parameter of this curve gamma. And E is the E is an Einbein which makes this the reparameterization, which guarantees the reparameterization invariance. So we get E gives the para. So it's the metric on the word line. Invariance. So now, of course, we could do the following thing. There's another version. This is also, we can use half of the equations of motions, right? Then we will get I of sorry, I've also forgot here the P. So if I write here I of Q and E, if I integrate out the P, so I eliminate the momentum, then I will get something like, sorry, by the way, I saw here there should be an E here. The E should be here and there should be 1/2. So now sorry about that. So then there should be an X dot squared, or Q dot squared, sorry. Q dot squared divided by perhaps E, maybe 2. And then plus M squared times E d tau. So that be, and then I can eliminate. So here I eliminated P, and then I could also eliminate E, and then I would get something like integral Q, I mean the metric G of Q dot d tau, and the usual geodesic action with N. So we'll start here. We'll start here or here, depending on. We can say we start here or possibly here. These are equivalent. Now the thing is though, now suppose I want to do the path integral. I want to do dq and E of E to the, say, I over H bar I. I will see immediately that I need to gauge fix, right? Because there's this redundancy of, I can take delta, so this has a redundancy, which means that delta Q is equal to Q dot times epsilon, so let's say tau goes to tau plus epsilon of tau, small reparameterization, and then delta E is something like E times epsilon dot, I think something like this. So that will be a redundancy, and therefore I have to gauge fix it. So therefore we will see already there will be some BRST system which will give you some ghosts and so on. So there will be some BRST invariance in this action, in this word line action. Fine. But here I want to not go into too much details about this. I mean, this is somehow maybe not well known, but nevertheless, in principle, a very old story. But the result of all this, so after doing all the work, we end up with some BRST charge. Let me write it perhaps as Q now, which is going to be C, I guess, minus C times P squared plus M squared. And that's it. So now where C is an odd variable, C squares to 0. So C is odd, so parity odd. And I guess there's not much more I can say. The thing is, obviously, clearly Q squares to 0 as a BRST charge should, but it's sort of trivially 0 because C squares to 0. There's really not much to prove. Now you can say, okay, you could start with this, you can take this theory and you can work away and you can see what is the cohomology of this Q. So this should really be, perhaps, is related to this omega 1, which we had in the expansion. There was a question, I think. No?
What is P in this?
Oh, P, sorry, I didn't define it. P is just the momentum conjugate to Q here for this point particle. So here. So I take here, it's just, so P, sorry, eliminate P by P is delta I by delta Q dot. Or delta L, I should say. Huh? But maybe I should say, you know, if I write this as integral L d tau, and then I take P is dl, sorry, by dq dot. So it's the usual momentum conjugate to Q.
I see. So we express it in terms of E and Q. Is that correct?
That's right. So once I eliminate the P, I will get an action which is a function of E and Q.
Okay, thank you.
You're welcome. Okay, so now it turns out this theory is not very interesting. You know, you can do this, you can play this game, you will find not much interesting because there's really no gauge invariance in this theory. This is a point particle, it's a massive spin 0 point particle, nothing else. So we don't expect any interesting gauge symmetries in this theory. Nevertheless, there is some redundancy, and the redundancy is related to this reparameterization invariance here, the one which I described here. There is some redundancy in the system, but it does not really describe a gauge symmetry. In fact, the cohomology of Q just means that you satisfy the field equation for the scalar field which you will get. We don't have to go into it because there's nothing really much interesting there to say. So instead what I'm going to do is I'm going to generalize it a little bit. I'm going to say, let me assume this point particle has not just a reparameterization invariance, but a super reparameterization invariance. So there is some supersymmetry in this theory. It's a word-line supersymmetry. So that means I will have a transformation where, okay, let me maybe write that. Let me write down an action and then discuss it. So that would be here. Let me take a slightly more interesting case, and I take this to be, say, Q. What will I do? I will take this formulation. And then I will also add some, say, theta, which are word-line fermions, and a super partner for the E. And then the action will look something like before, P Q dot minus E over 2 P squared plus M squared. But then there will be extra terms. There will be a term like plus theta dot. Plus there will be also a term, also there can be also term theta dot, and then there will be terms of the form, let me by the way take the mass equal to 0 to make things simpler. Then there will also be a term which is chi theta p. I can write such things. And now, for those of you who have already been in touch with supersymmetry, this is precisely what one expects, some sort of supergravity. You have a Einbein, which is somehow that would be the metric in gravity, and you have here what would be the gravitino, which is the super partner of the Einbein. So let me call it gravitino in 1 dimension, in 0 dimension, only time. Gravitino. So we mean that by this I mean I want to have the invariance. This system has an invariance which is as before. I have the delta E is something like E times epsilon dot. But we also can have, let's be 1 parameter, but then I can also have a, say, kappa times chi. So now I have 2 parameters, epsilon and kappa. So one is even, one is odd. So this together gives me a supersymmetry in the sense I have a super translation variance, I have an even and an odd, plus other stuff. Okay, so this is all very nice, and one can play this game. Is exactly more or less what one does in string theory, but let's not worry about the details because it's really not that important here. But at the end of a long day's work, what you'll find is that the Q, the BRST charge, will be minus C times P squared. I take the mass equal to 0. And then we get a gamma theta times P. Let's put a bar. Okay. should say a little bit. Okay, let me write and then explain. Plus gamma bar, theta, and then plus a b gamma bar. So let me explain a little. What do I have? You have lots of stuff, and here I forgot something. Here, p. So, okay, and I should remove this vector sign. So, okay. So what have I done? I've cheated a little bit. I introduced not just one supersymmetry, but more than one supersymmetry. So that I put here an I. I sum over I. So that means here I have to sum over I, which means here I should also sum over I. So I have not just one supersymmetry parameter, but more than one. So I have an extended supersymmetry. I don't have to do it, but it makes things more interesting. So let me take the simplest case is let me take I equal 1 and 2. So that is what we would say is an n equal 2 supersymmetry on the word line, simply because I have two supersymmetry parameters. All right, so great. So we have this, and then the gamma, so then I can form linear combinations. I can say theta, I take it to be theta 1 plus I theta 2, and theta bar, I define it as theta 1 minus I theta 2. So then you can take this complex linear combination, and this is what these guys are here, the theta and the theta bar. And the gamma, these are the ghosts. The C, and these are the ghosts. Now, since the C ghost we had already previously corresponds to reparameterization, which is how to say an even symmetry. It's therefore the ghost is odd, parity odd, whereas the super reparameterization is an odd symmetry, so accordingly this will be an even ghost. So it doesn't square to 0. So we have c squared equal to 0, but gamma, actually I can do the following, c squared equal to 0, and the cb plus bc is equal to 1. That also explains this guy. And then I have similarly gamma squared is not equal to 0, but I have a gamma with beta bar commutator now is the same as gamma bar beta, and that is equal to 1. And here should not be 0, so here should also be 1. So this is the story. So these are even variables, the gamma and the beta. The betas I've introduced here, they don't appear here at all, but they are just the conjugate variables to the gamma. They don't appear in the BRST charge, but they nevertheless are there. Fine. So now this turns out to be, this is the BRST charge for this more interesting model. Okay, so well, is it more interesting? It still squares to 0, not too much to do. But now we can say, well, let us now suppose this theory, I want to place this spinning particle. We call it spinning particle because the theta, because of the presence of the theta mu's. And we will see it right now in a little bit why. So I can ask, can I place this particle, which is described by this word line action, in an arbitrary background field while preserving the BRST invariance? And the answer is no. What you'll find is the consistency of this theory implies conditions on the background fields. And in this particular case, it implies the Young-Mills equations or the Maxwell equations for some background fields. So let us see how this comes about. So for this, I do this. So what up any space, what I'm going to do is, there is a trick. I'm going to do the following thing. Yeah, take this away. I'll make myself some space. No, what did I do? Let me try again. Smaller. Sorry, today's not my day. Try again. There we go. And then remove it. There we go, in the corner. So, sorry about that. So, now I have more space. Okay, so now what I can do is the following thing. I wrote, unfortunately, let me write it again quickly. I write the Q as minus C, and now I write here pi squared plus gamma theta bar with pi plus gamma bar theta with pi plus b gamma gamma bar. Now what is pi? Pi mu is equal to p mu plus a mu, some connection. To allow for some connection. Can be matrix valued or not, can be Lie algebra valued or not, but that we can decide. So now I can ask, what happens to my q squared? And let me just compute it. And what you will find is that q squared equal to 0 implies f mu nu, which is equal to d mu a nu, or so just the commutator of the pi nu equal to 0. So it seems it's impossible to actually couple this particle to any background fields in that sense, if you want to think of this as some background Maxwell or Young-Mills theory. Seems to not be possible. However, there's a trick, and the trick I think was found by Warren Siegel with his collaborator students at that time, I think. And the idea was the following. He said, well, this Q better act on something. I mean, this BRST charge should act as an operator, let it act as an operator on some vector space. So we introduce, because so far, maybe I should say that here again, so far, here we should say that Q, is built out, is an element in an algebra A, which is spanned by what? It's spanned by the momentum operator, apparently, the C goes, the B, the gamma bar. Then what else do we have? These are the generators, or generator, I should not say span, it should be generated. Generated. So, generated by this. What else did I have? The theta bar. Did I forget anything? The P. Maybe I didn't forget anything. This is an associative algebra. Well, we can think of it as a Lie algebra. Lie algebra, or a super Lie algebra. Because if we go back to what we had before, see here, we know that P and Q form a Heisenberg algebra if you quantize. We know that the C and the B's, they satisfy, this is a Weil algebra. This, yeah. Algebra, that doesn't, algebra. So, but there is some graded Lie structure here, right? So gamma with beta, this is a graded Clifford algebra. Then the theta also, I didn't say, the theta nu bar, anti-commutator is equal to delta mu nu. So it's a Clifford algebra. So after all, it's a graded Lie algebra. So we can think of Q as just abstractly to be an element of some graded Lie algebra. And we can write the nilpotency condition, Q squared. We can write it as 1/2, since it's an odd vector field. We can write it as 1/2 Q with Q, anti-commutator. And we would like this to be equal to 0 in order to have BRST. Okay, so far, then we have just these, what this word line theory gives, you see, and that's the point which I would like to make here, is this, the word line theory for us is just really a motivation to introduce a graded Lie algebra. Tell us what are the generators of this graded Lie algebra. Of course, if you tell me, find the graded Lie algebra, I will start working away and produce all sorts of exotic algebras, and they will be probably useless in most cases. However, here we do know that this algebra, which I took here, it originates from the propagation of some spinning supersymmetric word line theory. So similarly in string theory, you have the Polyakov action, or in the superstring, a supersymmetric version of the Polyakov action. We know it describes something physical. It describes the propagation of a string. This thing, somehow, this word line action describes the propagation of some point particle with some extra supersymmetry associated to it. So there is some physical connection. So this gives me a guide. So basically, this point particle gives me a guide of what is the right algebra to look at. And then I say, okay, it seems like this super Lie algebra is somehow a reasonable algebra to look at. And then I say, I could ask the following question: write down the most general element, in this algebra such that this is satisfied. So a nilpotent element of the algebra, you could say. Okay, we could do that. I'll come back to this again in a moment, but for a moment, let me go back first. First of all, what I want to do is I want to deform it. I know already this is one. I found one. I found one such element. Okay, that this is equal to 0. Sorry, I mean this is satisfied that this is equal to 0. I already found one. I just look in the literature of the spinning particle. Here I know this is one. This squares to 0. So I already found such a nilpotent element. Now we can ask, what are possible deformations of it? Can I deform this element such that I preserve nilpotency? And what does it mean? So basically that's what we're going to do. The way we're going to deform it is we're going to couple it to background fields. And by this I mean we introduce connections like this. That's one way of introducing background fields. Then you could say, okay, great, that's a well-defined problem. Take a nilpotent element in this algebra, deform it in such a way that nilpotency is preserved. What does that imply on the couplings? And so that seems like a well-posed problem. And the answer is, which Siegel found, is that, well, there's not too much you can do. You can actually introduce such a deformation, but you will find that the coding, if you want to interpret this as a vector potential, the corresponding field strength has to vanish. So then you would say, okay, this seems to not lead anywhere interesting. You don't get any interesting equations out of this. So now, what Siegel noticed, however, let us represent this nilpotent or this element Q. Let it act on a vector space. So let Q act on some H vector space. So, okay, well, if it doesn't square to 0, maybe it doesn't square to 0 on this vector space either. However, then he noticed another thing. He said, well, let us go a little bit further. Let us reduce, let us specify precisely what this vector space is. And what he said is, well, let us do the following thing. Let us assume that H is generated by polynomials in, what did we say, in theta, C, gamma, and beta, and P with coefficients in, say, L2 of R, of Rn, say, some functions. So quickly, let me write down an example. I take phi, for instance. I take.
I'm sorry, the beta B.
I'm sorry.
Or is it something new? The beta, is it B or is it something new which hasn't been introduced before?
I think this has been introduced before, but the point, I'm going to make a point which I think is due to him, I think, which comes only, and is the following thing, is let us take an element of H to be of the form, then we have something like a mu of x, theta mu, plus, say, we could write something like this. What else could I'm just trying to think of little bit at a loss. So I can take something like this, some function, I just denote it by some function of x times beta plus perhaps, it just has to be a little bit, yeah, I can write other functions, g of x times gamma and so on, these kind of things. Right? But if we could also have some, let me write here maybe g1 of x plus g2 of x gamma squared plus g3 of x gamma cubed. And also, in fact, you could take perhaps b mu nu of x, theta mu, theta nu. So that's what I mean by this, by this condition here. It's just some polynomials in theta, c, gamma, beta, and p mu, with some coefficients which are space-time functions. I wrote here x, I mean x is the same as q, sorry. So note perhaps that there is no, maybe I put that in red, no theta bars, no gamma bars, no beta bars, and no b. So that's like a Fock space construction. You say these are destruction operators, and the thetas, the betas, the gammas are creation operators in that sense. Okay. Now, this doesn't yet do the job. It doesn't, as you were saying, Ondra, that's first of all not very new, and it doesn't do very much. But now he goes further and said, let's restrict it in the following way. Let us assume it can only be at most linear in any of these fields. So this is gone, this is gone, this is gone. Let's assume it can only be linear in any of these generators, not fields. Let's assume that is our vector space. We just reduce it in such a way. We decide that our vector space, that's what it is. And then ask for the condition. Okay, let me see in its space. I can now put it here and ask for the following condition. Demand that and impose that q squared restricted to this red subspace, let's say this is H0, this defines H0, is equal to 0. You only impose this on the reduced vector space. And then what he finds, well, he finds that this implies d mu f mu nu equal to 0. Maxwell equation for the vector field. And in fact, there's also Orion-Wills. If you take the algebra value connections. So it seems like there is a procedure, and you see one has to do quite a lot of stuff. One has to do the following thing. One has to reduce somehow the vector space on which this Q can act, and then you can get the Young-Mills equation. So basically, what is the lesson that we've learned? The lesson that we've learned is that if I take the algebra, the superalgebra, which is given to me by the spinning point particle, and I construct all possible, I consider all possible elements in this algebra, I will basically not find any interesting physics. I have to reduce it. I have to reduce, and how can I reduce it? Well, the one way to do it is that I say, okay, let me formulate this in a different way, perhaps. Can I put this in a little space? I think I can do it up here. This can go. Also have to be careful not run out of time. So there's an equivalent way of saying what I just said in terms of purely the algebra. So we can say if A was the super Lie algebra which we considered, what we can say then is we define let's define a double prime to be how should I say this? All the elements in A just 1 second. Circle here. Yes. So by all the elements such that A acting on an element of H0 is equal to 0. So that is one way of reducing. So that's one way of reducing the algebra. So I don't want to consider all possible elements, but only those. Actually, I'm doing something wrong here. I'm very happy. I think I'm even saying something wrong. Let me look at my notes because sorry about that. It's not quite right. Only 1 second, it won't be long. Apologies. Yeah, sorry, I didn't see. Yeah, now it was up now. Now I got it back. It should preserve. Sorry, it's too big. So I want to have it should preserve H0. So now it's so that's a condition of the algebra. It should preserve this space H0. So that means, for instance, if I have an element psi, which is of the form theta mu, a mu, remember we had, and then I act with, say, a onto this psi, I should not, and then if I get, for instance, theta mu, a mu times some gamma, for instance, then that is not a good element because this is no longer linear in the generator, so therefore it should be excluded. So that is the condition. And then I can take an ideal, or I can take a quotient. I simply define, so to say an ideal first, sorry, there we go. I define an ideal, which is given by all the elements A in A, so which annihilate simply, for which that is what I had before, incorrectly is equal to 0. And then I can take a quotient, A prime, I divide it by this ideal. So that is a way in the algebra of saying what we're doing. We're reducing the algebra, but first of all, we take a subalgebra of elements, which preserves this space. And then I quotient out the algebra by elements which annihilate this space. And on this, if I ask now the question, if I demand that Q is an element, Q first of all is an element in A prime, and Q squares to 0 in A prime, that implies Yang-Mills theory. So that was, I mean, this thing is, by the way, I should say this is something that's not Siegel, that is together with Maxim Grigoriev and Adil Meyer. But the result that to introduce this smaller vector spaces, that this, I mean, now I can put this properly, the fact that you can get some interesting physics out of nilpotency condition on a reduced vector space, that is what Siegel's contribution was.
Ivo, can I ask?
Yeah, I should stop. Yeah.
No. I'm not stopping you. I'm just asking a question. What happens if you choose a different vector space? Like, I mean, okay. This is one, right? But you could choose others.
Yeah, that's a very good question. So now let us assume we choose a different vector space. So let me replace it by some H prime here. Then you will get different physics. In fact, what you could do is there is a choice where you can get, for instance, where you can get two forms rather than vector potential. So the physical theory that you describe is the theory of some two forms which satisfy first order constraints. So there's other examples with H prime, and here just to give an example that there you, instead of some A mu, will be replaced by some, say, B mu nu, which will have to satisfy D mu, B mu nu equal to 0, something like this. But these are, so that would be another possibility. So it's absolutely a good question. There is some freedom in this choice of A prime or this H0, which can give you different physics. So there is absolutely.
Okay, thanks.
Let me, by the way, say one thing, that the H0 which we've chosen has an interpretation in string theory, and it is related to level truncation, which is something very popular in Prague, but more in the Institute with Martin Schnabel's group, is level truncation. Level truncation, well, that just means you throw away most of the modes of the string, and you have to see whether it's consistent. String theory, it's not consistent, it's inconsistent, but you can do it anyway. Here it turns out to be consistent. So now that's the story. So now let me see, I should really stop probably. I mean, I have a little bit more to say, but it depends on how much patience you still have.
We started a little bit late, so I mean, you could still keep going for another 5 minutes or so? Or?
5 minutes will be fine.
Okay, perfect.
Thank you very much. So now that's the story. So now you could say, as you were already pointing out, you could change this, this ideal, or you could change this reduced physics. You can get different physics. Doesn't seem there's too much interesting physics actually, as far as I can tell, by changing it, other than these young wheels. But that's the story. Now, but another thing you could do is I have taken n equal 2 word-line supersymmetry. Suppose instead I take n equal 4. So I take 4 spinners on the word line rather than 2. What happens then? And you can play the same game. So now what happens is, oh, I should perhaps say one more thing. There is a natural way to characterize this H0 in n equal 2. Because you have an n equal 2 word-line supersymmetry, you have an SO2R symmetry which rotates these two spinners into each other. And SO2 is the same as U1, and U1 has a conserved charge, and you can just say H0 is defined by fixed charge with respect to this U1, which is this U1R symmetry of n equal 2 supersymmetry. If I took n equal 4 supersymmetry instead, I have an SO4R symmetry because I have 4 different spinners on the word line, these θ's. So because I have θ I, and I is equal to 1 to 4. So now that gives me more freedom of producing such a H0 because I have more generators in here. And we know, for instance, the SO4, I can use it as equivalent to SU2 times SU2. And then you see, I can take different condition. I could, for instance, do some restriction, fix the charge with respect to some SU2 here, or with respect to SU2. There's much more freedom. There's a neat way to represent that, is that if I look again at the vector space psi, which is an element in H, it will be of the following form. It will be, it will be of the form, say, let me write just some term, A mu1 to mu n, θ, mu1, θ, mu n. And then I can also have still here I and j, and here I can put I and j, I1 and so on, I1, and so on. So, but there's a way we can just use the Young tableau. So the general state psi is of the following form. Will be, that's somehow one copy of this SU2, and then I have another copy of the other SU2. So, and now we can start putting restrictions on it. So, and the restrictions are, I can, for instance, say that you should only have, for instance, only one box. So you could assume that I could only have one box here. But then I could say, well, okay, then I can say, I can throw out the symmetric part or the anti-symmetric part, which left. So then I would have some theta. So then I could say, I only want to keep the symmetric or the anti-symmetric part, or I will only keep the trace or the traceless part. And all these choices correspond to physical fields, and they correspond to some anti-symmetric tensor field, if you take the anti-symmetric part, a symmetric tensor field, if you take the symmetric part, and if you take the trace, it corresponds to some scalar field. So what I'm trying to say here is, depending on how you reduce this vector space, you allow for a different amount of background fields to which you can couple. So depending on how you choose this, how you choose this space, that connects to the question before. And you know, the simplest thing is that not to bother at all. Just to say, I just take everything here, symmetric plus anti-symmetric plus the trace and traceless, everything. Then what you get is, this is the Calderon field of string theory. This is the metric of string theory, and this is the dilaton of string theory. And the equation of motion which you get is now not the Maxwell action, obviously, because there's no Maxwell field, but what you get are the equations of motion for type 2a supergravity, turns out, including the dilaton. Type 2a supergravity has a metric, has a Calderon field, and has a dilaton, so the Neveu-Schwarz vector. You also have Ramond-Ramond fields, but we don't consider them. So then the upshot is then this point particle, supersymmetric point particle, n equal 4 supersymmetry, contains all the equations of motion of the effective action of string theory. So that is interesting in two respects. First of all, it seems, yes, we usually say string theory is one consistency check of string theory is that it reproduces Einstein equations plus generalizations, which are the supergravity equation. That is true, but so does the point particle. So you don't really need a string for that. Point particle makes the same predictions. Which is perhaps also not totally surprising, because the point particle is the one that couples to massless fields. On the other hand, what we have, going back to the very beginning of my talk, because now I should really wrap up, this construction which I've described is completely background independent. I've never assumed anywhere that the metric is flat, that the Young-Mills fields are 0 or so when I made this construction. So you can actually get this homological vector field. You can for the point particle, we can construct these homological vector fields, and we can find the critical points. I just described to you the critical points are the solutions of the supergravity action. But the supergravity action is not obtained in this case as something that reproduces the S matrices of some Feynman diagrams. It is simply obtained by imposing that the BRST charge is nilpotent, which means that the theory is quantum consistent. Quantum in the sense of normal or no loops here, of course. So it is possible for the point particle, you can go all the way back here. And for the string, of course, this also perhaps clarifies a little bit why we will maybe never be able to do this for the string. Because you see, even for the point particle, it was quite tricky to realize or to understand. Where is it? Let me get it. I will find it again. Where did I put it? Here. Even for the point particle, it was quite tricky to identify a suitable subalgebra, a double prime, of this huge algebra which is given to you by the point particle, and the suitable quotient so that the interesting physics is contained in it. For string theory, the algebra that you obtain is infinitely much bigger, and I have no idea how to identify the analog of this a double prime or the a prime in which the interesting physics would be. So I think that mathematically speaking, that's where the challenge is. So you could ask the following, you can pose the following problem. Given a Lie algebra, super Lie algebra, what is the BV action that corresponds to it? To a nilpotent element. And that is basically what we're trying to answer here. And we are able to answer it for some very simple examples, which are the spinning point particles. And maybe one can go a little bit beyond ambitwister strings. I'm not very hopeful that all this could be done for the full string theory, but that's how one could go about it. And that's perhaps a good place to start.
Okay, so thank you, Ivo. And if you guys want to show your thanks, you can feel free to unmute yourself and give a round of applause. Yeah. Okay, so I'm sure there are many questions. I might start because I have the that right, which is great. Actually, no, I'll open it up to the floor. Let anyone else talk. Are there any questions?
I have a question about the. So when you perform the deformation of Q and reported the potency, the full nonlinear equations of motion of supergravity, or just some part of it?
Yeah, no, you get the full nonlinear equations. Yeah, I mean, you don't get higher curvature corrections. You don't get R² terms or things like that. But at the class, you get the full classical action. You get equation. I mean, you get Einstein's equation, for instance, with the full nonlinear one. Yeah, so that's the nice thing. You see, it's not perturbative. It's really truly, in that sense, in terms of background fields, it's truly non-perturbative. You don't expand around the certain background.
Ivo, do you get any restriction on the dimension?
No, that's another good question. So this, and I mean, on the one hand, it's perhaps clear why not, because the restriction on the dimension in string theory comes from the central extension, right? Which you get when you do the BRST algebra, you get the central extension. You want it to be equal to 0, so that gives you restriction. Now, we don't get a central extension here because it's just normal. You see, we just have normal ordering, but we don't have any any interesting stuff like that.
Mm-hmm. Yeah. Okay.
So it would work in any dimension. You can also get, maybe I can say, there is a little bit, I was saying that this point particle predicts the equation of motion of string theory is true. It's a little bit incorrect in the following way, is that there is the possibility in the point particle, provided you project out the Kalb-Ramond field, there is the possibility to introduce a cosmological constant. So you could have a de Sitter background.
And can you get Ramond fields?
Ramond fields, we didn't do it, but I think you could do it in the following way. What you would have to do is, I can explain that quickly. Some space, a little bit of space here. So what we did is we took, we generated our vector space psi. We said it's going to be some polynomial, we said in theta mu, gamma, c, and so on. And then acting, you can think of this as acting on some constant functions, which are the vacuum, which just be constant functions. And then you can take some functions here. But of course, that is the sort of analog of what you would say it's the Nebel-Schwarz sector of string theory.
Sure.
If I wanted to mimic the Ramond sector of string theory, I would instead say, I'm not saying this, but what I'm going to impose is that there is some ground state, S, and then I impose that the theta mu's, for instance, will be equal to 0. Huh? So you know that. So it's this thing. So we could also we haven't used this possibility. But if you work with this realization of the vector space, then you would get either depending on the number of supersymmetries. If you take the n equal 1 word line, you get just fermions, space-time fermions. If you take n equal 2, you will get, or n equal 4, you will get Ramond type fields. So you could also do, but it's awesome. You have to do the Ramond sector. So
Cool.
That's true.
Okay, are there any other questions?
One more question. N equal 2, or probably goes on the same line, but N equal 2 to define theta and theta pi, you need complex structure in your typing space. one and to define data into a complex structure. Can you incorporate this as a deformation of Q? Like, can you deform Q in a sense of the complex structure in the target space and introduce this as the deformation of the Q operator?
Mm-hmm. Okay, so let me, the acoustics is not very good, but let me repeat maybe if I understood. So is the question, can I also consider the deformation of the complex structure of the target space as some of the background? Yeah. It's an interesting question, and I don't really know the answer. I think one would have to, it's conceivable, but you probably would have to produce some sort of Chern-Simons type theory, which means, you know, you'd want to produce, I have given it some thought, but let me remember what was my outcome. So how do I get this first order system? Let me remember. I don't remember, but basically, it's. Unfortunately now I don't remember what I came to. But you know, you'd have to. I probably, if you were able to produce some Chern-Simons type models in this way, which I'm not sure you can, but I think you should be able to. Then I could see that complex structure would enter in the deformation. I mean, there is one way. Yeah, I think again, maybe one way is to better understand the connection of this theory with this zombie twister string, but because there, that's easier. So, and I think there's some close connection, but I don't really understand it yet. But I mean, the answer is probably, I think yes, but I don't know how to do it right now.
Okay, so I guess if there are no more questions, let's thank Ivo again.
Well, thank you. Thank you for having me.
Thank you.
Thank you.
It was nice to be there.